Welcome. I'm Brian Beck, partner at Zuber Lawler. Thank you for joining. Zuber Lawler is a law firm with offices across the United States in 8 different cities, doing a lot of work in a variety of technologies, and we are exceedingly excited about emerging areas of technology that will drive the economy 10 to 20 years from now. DeadCatLiveCat is an online quantum computing magazine founded by law firms BLG in Canada, Marks & Clerk in the United Kingdom, and Zuber Lawler in the United States. We're attorneys, but we're also scientists, engineers, and futurists focused on the likelihood that quantum computing, coupled with AI, are going to fundamentally change our world within 2 decades. We have with us here today Himadri Majumdar and Janne Lehtinen, co-founders of SemiQon, a Finnish quantum computing company. SemiQon is, according to its founders, focused on building, quote, silicon-based quantum processors for the million-qubit era, and we'll talk a bit about what that means shortly. Himadri and Janne, welcome to the program.
Thanks for having us.
So to begin, Himadri and Janne, could you tell us a little bit about yourselves and your background?
Sure, I can start and Janne can continue after me. So hi, my name is Himadri. I am the co-founder and CEO of SemiQon. We are 4 co-founders who started the company in 2023. We'll talk about it later. As for myself, also Janne, we were employees or in various roles at VTT, Technical Research Center of Finland, before we started in the company. I myself I do have a PhD in applied physics from a long time ago, but I have been involved in innovation management for the last 20 years in different roles at VTT, being a senior scientist and doing sales, technical sales, and also leading a sales team. And finally ended up being the program manager for quantum tech at VTT. And that's after that, we started the company. We'll tell more about the company later, of course. But yeah, so that's how it is. That's about me.
So I'm chief science officer at SemiQon, and I've stayed more on the technical track. So I worked in various roles also at VTT. The latest one was research team leader, quantum systems team, where we had something like 20 persons working on various quantum devices. I have personally experienced more than 10 years of various kind of microelectronic and quantum devices, mainly on the superconducting side, but then let's say past 5-6 years, I've been more and more focused on the semiconductor side, and this is of course obviously now the main focus and where I think we should kind of put our bets on.
You mentioned VTT and that SemiQon's a spin-off of that. And I get the feeling that in Finland, that is somewhat of a household name, or at least a household name among scientists. But for those of us outside of Finland, what is VTT?
Yeah, so VTT does basically science that bridges the research that's done in universities to industry. So the idea is to do applied science that benefits, let's say, Finnish society, and then of course overall the society. And here, of course, one part of one target of the organization is to have spin-offs like SemiQon to take the research that has been done and make it industry that then will have the significant impact in the future.
So how did both of you get into the quantum computing field? Start with Himadri this time, I guess.
Yeah, sure. So my involvement with quantum computing as such is new. So I started getting interested in the topic, let's say around 2019, and then more actively when I took up the role of program manager for quantum technologies at VTT. But I think we need to go a bit back on quantum computing or quantum technologies, as I would like to call it, because even when I was in a scientist role or in the sales role, we did not explicitly call it quantum computing, but things were actually happening already then. We called it quantum 1.0. So squids and other components were already made based on quantum phenomena. So in that sense, I think we have been exposed to this for long, but actively pursuing quantum computing in my case, I started in 2020, 2019 during that period.
Yeah, for me, the kind of joining the SemiCon was more that I kind of saw that in research environment, we couldn't progress the technology fast enough. So for me, it was that I want to put now all my effort in making this reality. And this was why I wanted to join SemiCon and start driving this fast forward.
And what made the two of you decide to form SemiCon as a spinoff from VTT?
Yeah, I can take that story because I love telling that story to everybody. So yeah. So like Janne said, he was the team leader at VTT, working on both superconductors and semiconductors there. And being on the program manager role for myself, I was looking at it from a broader perspective. So I was obviously, one aspect of my job was to lead the quantum computer build project, which was happening at VTT based on superconductors. But I also figured out or found out that semiconductors were very interesting at that point. And Janne and others were actually doing some cool stuff there. And what we started was sometime around 2022 when we got together, four of us who we co-founded the company later. And one of them was Professor Mika Purnila, who is 40% in in SemiCon, but the rest he's still a professor at VTT, and Mark Kukain-Lauri. We were brainstorming what to do with this technology and how to bring it forward and make it a potential candidate for quantum computing. And it sort of snowballed from there. I personally never had an intention of starting a company, honestly, but it was a fantastic opportunity. And with the team that we had, we were really excited, and we had some good, let's say, IP on strong things. And that sort of started things. We started discussing with investors and so on. They were interested as well. So it just built from there. So it's kind of like not strongly in the focus of building something that is not a company, but it was the idea of building some new technology. But it evolved into a company through the process. And I'm glad we did that, because I think we are achieving more, like Janne said, we are achieving much more than we could have done in a research environment there.
So getting into the technology, I know SemiCon is working on silicon-based spin-qubit chips. For the layperson, what is a silicon-based spin-qubit chip?
Well, silicon qubits, those resemble a lot like standard transistors that we have in our everyday electronics. So there we control by gate potential whether the transistors conduct or not. So whether it's classical 1 or 0. But then if we can isolate just single charge carriers to these transistor kind of elements, we can use its spin property. It's kind of like a magnetic property of particle in some sense. And use this as qubit. So the spin can be either up or down. So it kind of makes natural qubit bases. And when we isolate many of these in a system, like we have in mobile phones, transistors or other elements, we can make large systems of spin qubits and couple them together. The control of these systems, it's a little bit more complex, and this is of course very simplified view of the system, but in principle it's like standard electronics just taken to quantum. Right?
And what are the advantages of that qubit design compared to competing quantum chip approaches?
Well, one of the biggest is the fabrication technology that there. So trillions of dollars have been poured in developing these fabrication techniques that we use for modern silicon devices. And basically, we can use all of that. Then it also comes to the scalability aspect of the qubit size. So our silicon qubits are very similar to those transistors that now can be fabricated billions on a chip. And similarly, basically, you could do these qubits there on these quantities. And this is not that all the different quantum modalities can do. So for example, if we compare to superconducting qubits, transmons, the area that one silicon qubit uses, it's roughly 1 millionth part of that what is on superconductors. So there is huge potential in that sense. And then the third one is that we can operate these at higher temperature. It's still cryogenic temperature, but let's say 20 to 100 times larger temperature than with superconductors. And this enables that we have significantly more cooling power, so up to 10,000 times more cooling power available for the system. And with the cooling power, we can have larger system operated. And this again comes then to the scalability. The fourth reason why this is the technology that we think is going to succeed is that we can combine the classical processing easily with the quantum bits. As already mentioned, the qubits are like these transistors. So you can make the standard CMOS transistors and qubits on a same chip and make them work together, making the control part also on a chip, which then makes it much more economic and compact and sustainable to be used.
Putting the qubit part on the same chip as the classical electronics makes it easier to integrate the quantum aspect with the classical computing. Is that what they're?
Yeah, in principle, like a quantum computer is never kind of standalone units. It always requires classical computing there. And let's say classical control more than computing. The computing, we still envision that that's done at room temperature because it's just better and easier to do there. But you also need plenty of things to control the qubits. And this can be done there at cryogenic temperature. And currently, let's say, well, maybe even 90% of the cost of the quantum computer comes from the control and not the qubits.
What are some of the unique challenges that the silicon-based qubit approach has relative to the other competing approaches like superconducting qubits?
Yeah, so the unique challenges, those are also related to the small size of the qubit. So when you have the qubit small, it's hard to control it also, because you need to do it really, really locally. And this makes some technical difficulties. It's more of an engineering problem, but still it's a problem. And then also when the qubits are small, if there are defects in your system, you sense those locally well. So if the qubit is large, single defect cannot affect it too much, but when it's small, it can affect. And this is kind of the problem. We need to make really good devices in order to make them work. It's kind of double-edged sword kind of thing that you have the great potential, but then you need to pay something for it.
Now, as part of the kind of advantage of using the already known silicon-based semiconductors and integrating them with your qubits, how does SemiQon leverage the existing semiconductor fabrication technology to advance its work on its unique qubit chip design?
Yeah, so we work on CMOS pilot line, and the CMOS technology is the standard silicon processing technology. So basically, what we are doing is using the industry standard processes, but just tailoring those to be better suited for these qubits. So basically, everything we do is immediately scalable to industry scales. And that's one of the really big advantages. Then what we gain kind of for the performance of the devices, there, of course, it is that these processes have been studied for decades. So everything is highly established. When we face some problem, there are kind of the history already knows the solution in some sense. We just need to identify what are the problems, and then we have the solution book there already ready by the extensive research that have been done already.
What I would like to add something to what Janne said, and this I think is a bit more specific related to semiconductors, and that's infrastructure, right? So Janne mentioned about these fabs which exist that has been invested in order of trillions, and they are now manufacturing stuff for the classical era. But you have to understand then, how does a small company like us dare to do things like that? So how can we afford such infrastructure to build a product? And herein lies the very important and let's say fact about Finland. And going back to the point that Finland has been investing significantly in public funded pilot lines for semiconductors. And we are actually operating out of one of those. So even though we as a company are not investing in the infrastructure already exists, and we are the beneficiaries of it. So we are just pay-per-use user for the facility. And it's a fantastic opportunity, because in many cases we see both superconductors, semiconductors, and others, the fabrication facilities are, for university spin-offs, it's in university environment in most cases. Or in some cases, they actually go to foundries to ask for services. And one is expensive, the other is time consuming. So in our case, having access to such a facility actually allows us to do things in scale, in an industrial scale as well, and at a low cost. So it doesn't increase our burn rate significantly. We can still keep on developing things quite much into the future.
So does that access to industrial scale fabrication facilities allow you to kind of speed up the experimental cycle for fabricating your parts? And how does that accelerate your development and commercialization for your company's chips?
Maybe I take that again. So it's about the whole sort of domain of quantum computing is kind of like in an engineering race, because we know the science has been done and it has been proved. And now what we are trying to do is to pick up the speed of who gets to the engineering solution faster, right? So in our case, having such access to a pilot line and facilities allows us to do certain things faster. So for example, we know that the global kind of standard for silicon spin qubits have been that if you have a design, or let's say from the design to the fabrication, it takes about a year right now. And what we can do with our current approach of having the access to a pilot line is we can reduce it down to 3 months. So we can generate, or fab out as they are called, every 3 months of new generation of devices with iterations, and we can check whether they are fine, and then we can go back to the design table and do again. So in a simple way, we are multiplying it 4 times faster. So this is going to be a advantage from an engineering perspective, that how fast we can go to those solutions. So that's why it gives us a clear advantage in that case.
Now, in the development of its quantum chips, is SemiCon focused on kind of creating more general purpose quantum processors, or has SemiCon been working to optimize quantum processors for specific applications and use cases? Is there differential applications, or is it kind of focused on general quantum processing?
Basically, it's general quantum processing that we are doing the circuits for. There is, of course, potential of tailoring for certain specific problems. So the kind of fabrication of these devices is highly flexible. So in that sense, it can be done, but so far the idea has been.
I want to switch gears a little bit and talk a little bit about the SemiCon's role in the industry. Can you talk a little bit about SemiCon's collaboration strategy with partners in the quantum computing ecosystem?
Yeah, I think that's a very good and important question for companies like us, because as you said in the beginning, Brian, we are a company working on quantum processors, right? So we don't build quantum computers. So in that case, obviously we're interested in applications and use cases and those things, but we don't want to allocate resources for that, because then the cost of development and everything goes up, and we don't want to do that unless we are in a revenue stream where we can generate sufficient revenue. So what we are doing in a business model perspective is we are partnering with other expert companies in our value and supply chain, and we are building it together. So for example, we have a EIC, European Innovation Council funded project in Europe, where we are collaborating with a company in Netherlands called Qblocks. And they are working with us to build a demonstrator for a quantum computer where we will be the one providing the chips and they will be doing the integration with their control electronics and so on. So this is a perfect example of a collaboration that we look for. We also have other collaborators in the same way with various levels. And this is how we want to sort of fasten the progress, that accelerate the development, and everybody have their own set of expertise. They're advancing those, and then we work together. And that other aspect of our collaborative strategy is how do we use our chips, the early stage chips that we are making. So for example, we had a four qubit or 4 quantum dot chip that we announced a couple of weeks ago. And what we are doing is, because these are not chips that you can actually do quantum computing, because they are so sort of rudimentary as devices. So what we are doing is we are giving them to our partners, so our collaborators in the universities, because we believe there is a strong need in the academia to do research on these topics. And in many cases, the PhD students spend half of their lifetime building a good device. So we are making devices, good devices in hundreds. So in that sense, we are saving a lot of time for the researchers, and they can then go further on their research. They can build newer solutions, which once they do and publish, we benefit from them. So there is a selfish aspect of it, but I think there is a stronger community involvement in there. And this is how we are building our collaborator network as well.
And in working with those collaborators, how is SemiCon ensuring that its processors are compatible with other partners' products and can be integrated successfully with those other devices?
It is, of course, really important question for us, as we are not doing the full stack. So I think what's going to happen in let's say reasonable time span is that there will be similar approach as is on the PCs, for example, that there will be specialized components and standardized ways of communicating between the elements. And also this goes to the software level, so their standardization will be done. Of course, currently there is not too much of that. So how it's done is by providing information how things work, and kind of having the expert level interface and conversions done there. And this, I think, will be the mode of operation for some time, but of course we are trying to get to the standardized version. And I think one way to do it is to work with other companies, and then of course this makes the standards happen and realized when large enough quantity of companies do it.
Yeah, absolutely. And I can also probably say it here that it's very important, the standardization aspect, because the whole industry is kind of like a bit of wild west right now, and everybody have their own protocols, own standards. And for us, it is therefore important to also not just work and listen to the partners that we work with, but we are also trying to work with, for example, our measurement and testing facility is in a premises of a metrology institute, so which keeps standards on various aspects. So they are sort of extremely knowledgeable how to create standards, how to maintain standards, and so on. So that collaboration also benefits us as well, indirectly. And this would be extremely important. I think I agree. This was a very important question that you asked, Brian.
Within kind of the broader economic world of not just quantum computing, but technology in general, how does SemiCon see its role in boosting regional and global competitiveness in the field of quantum computing, in quantum computing relative to other industries, not just your company relative to other quantum computing approaches?
Right. Again, I think there are, I would answer it in two ways. First of all, I think what is happening right now is with the not just quantum computing, but the whole future of computing is going through a flux. So we are seeing AI computing coming up, NVIDIA doing fantastic things there. We are doing quantum computing ourselves. There is neuromorphic computing there as well. So different types of computing are coming up. And I am envisioning a change in guard in that sense. So if you remember the semiconductor industry, that propelled a small country like Taiwan to be extremely valuable in the global supply chain, right? So we recognize that now. And I'm hoping that this will happen with quantum and other computing as well. And hopefully the tide will be on the European side and the US side with this. So we will bring back the manufacturing on the Western side of the world. And this is very important because we, as a continent in Europe and also in Northern America, we are losing expertise. So there is, even though there is a lot of investment going on in the CHIPS Acts on both sides, there is a lack of expertise in these domains. So what I think is going to happen is by building quantum, by building other computing, we are going to bring those back. And then the second aspect is whatever we are doing in the classical computing side, we are actually catching up to the Far East. So they are way ahead. So we are trying to catch up. And quantum should be the leverage for us. We are good in quantum. So let's leverage it to get to the next generation of things that we can build. So in that sense, I think it's very, very important from a social perspective as well, how we deal with quantum computing.
Now, speaking about the both the future and the present/near future, SemiCon just put out a press release last Thursday about getting its quantum processor testing and measurement facilities at the VTT Mike's premises running. What does that mean for the future of SemiCon?
Basically gives us perfect infrastructure for our R&D measurements, and it's not just having the right kind of building with proper things there installed, but it's also getting the right coffee room discussions and being in the right environment to work. So I think it's quite crucial for our, let's say, R&D advancement and looking at the future of the technology.
So looking ahead to the next few years, what are the key objectives and priorities for SemiCon, and how is the company planning to continue pushing the boundaries of quantum computing?
Right. I think, the whole quantum domain, quantum computing domain is going to push boundaries as we go forward into this decade. And at this moment of time, obviously, superconductors are further ahead, and the quantum error correction or fault tolerant quantum computing with neutral atoms or ion traps are emerging, and they are going to push the boundaries further. But semiconductors are at a let's say, earlier starting point. We are, as I said, on the single-digit qubit era now. And what we are trying to solve right now is the engineering challenge on getting these to scaled up. And that's the work that we are doing now. And our hope or our vision is, if we are able to keep this growth path going, the speed that I mentioned earlier in that case, then we should be able to achieve 300 qubits or in that vicinity by the end of 2027. So that's kind of like our bigger target. And then doing the same kind of progress on the scalability, we should be able to reach 1,000 by the end of the decade. And then onwards, it's a bit of too much into the future, but I think it would be good to say that after this decade, we might end up in a Moore's law kind of situation where we double the qubits every year. And that will take us to 1 million qubits by the end of 2030s, so in the beginning of 2040. So I think this is kind of like a longer term picture that we are putting as goal for ourselves.
So going outside of SemiCon, what do you see as some of the most exciting recent breakthroughs or developments in quantum computing other than what SemiCon has been working on?
Maybe Janne would be a better person to talk about it technically.
Right, yeah, sure. Well, of course, what has been really exciting has been the progress in quantum error mitigation and even on the correction side. So those are something that we've been following really closely, and of course it's really relevant for our technology also in future. So I think this will be the path that leads to let's say practical quantum computing. It's probably not happening next year or not even maybe in next 4 years, but I think it starts to be still close that we can start to treat the quantum computers as kind of tools for actually solving problems that are practical and of high value for the society. So that's.
And for the layperson, what is quantum error correction and why does it matter?
Okay, yeah. So the qubits are very prone to errors, whatever the technology is. Those are typically not good enough to be used as is. So what we do is encode the information to many qubits, monitor it through this, and then also correct if error occurs to the qubit, so that we can still maintain the quantum state as was meant. And this kind of with this excess qubits, we can make the error-prone computer fault tolerant in future, and that enables them doing these large calculations that are required for practical quantum computing.
Now you talked about the move, the hopeful increase in the number of qubits that we can go work with from the tens of qubits that we're seeing now to hopefully thousands by the end of the decade and on our way to millions. What role do you think quantum computing is going to play in related fields, cryptography, material science, et cetera, as the field makes that progress from tens of qubits to thousands to millions?
There are already many envisioned applications there. So kind of physicists have been really eager to think about, do these mind games. And looking at the results, it seems really high impact for all these fields if we can get the simulations like working as was kind of how the theorists see it, so in perfect world. But of course there is still plenty of time before that happens, but even on short scale we can probably boost up the calculations, so make it more efficient and practical advantage. But the advantage at first is like exponential, or maybe it's 20% more efficient calculation for some problem that's to be seen. But I guess in long term we are going to see the full advantage, and then of course we can do things that we cannot even imagine at the moment. So gaining understanding that is not available, and I think the applications also when we have the practical computers will be quite different. So I think predicting the future technology is one of the hardest things there is, and not too many have been successful in it. So I'm not going too much on that road, but I think there will be plenty.
I agree. But what I would add on that is you mentioned cryptography, Brian, and I think there is a bit of atmosphere of fear around quantum disrupting the RSA and the prime number cryptography techniques. But I think the idea of Shor's algorithm being used in quantum computers to break those things are a bit into the future still. We are not there yet. It's things are improving for sure, and at the same time there are these post-quantum crypto algorithms which are being developed. So I do not personally think there is any reason to fear that there is going to be a doomsday scenario. But obviously, it's good to follow the development in quantum computing. We want to do that, and we as a community has to be open and honest about it as well. That where we are and what we are able to do with these machines. But I wouldn't say there is a reason for being afraid in terms of cryptography right now.
Speaking of future doomsday scenarios that people are scared of, the hot topic in classical computing right now, at least among the general public, if not necessarily computer scientists, probably them too, is the incredibly fast advances we've seen in generative artificial intelligence with large language models in the last few years. What role do you think quantum machine learning will play in the advancement of artificial intelligence as things go forward?
Yeah, at the moment, of course, it's even nicer to see what will AI do to quantum computing. So there is plenty that AI can be used in order to enable the quantum computing. Then, of course, quantum computers will be really good in parallel and optimization problems. So in that sense, it will boost the field a lot. This again will not happen, let's say, in next 5 years. It's still in future. But what it can do is to make it much more efficient. So we don't need to anymore scale up the hardware to really, really huge data centers in order to do the calculations that we need to do, but we can do those much more efficiently, consuming only a fraction of the power that's there. And of course, we can do much more complex systems also. So I think that's what quantum computing is going to do, but it's still in the future. Now I think AI will affect a lot more quantum computing than quantum computing to AI.
So you kind of touched on this a little bit in the last two questions, but what do you think the potential impacts on society will be of quantum computing as it grows in prominence over the next decade or so?
Right. We did cover the cryptography aspect earlier, and I mentioned about the societal aspect of bringing back manufacturing. Those are important things. But other thing I also have, it's related to the fear factor that I mentioned, and that's related to. I think it was one of the science fiction writers who said that if you do not understand something, it becomes magic, and quantum computing is pretty much in a magic state right now. So for a society to adapt and adopt to quantum computing, I think there is a significant need of education and educating, not just in the traditional way of it. Of course, we need more workforce. So we need to teach our younger generation to learn quantum, to understand what it is. You don't have to understand quantum physics to do quantum. You can do engineering as well. So there are many ways to be part of it. But it's also about educating or re-educating the workforce, that those who are doing AI or other things today how do they benefit from quantum in the future? So that kind of training is needed. And the other aspect of training is for the policymakers, for the decision makers, that I know and I understand that quantum is a very, very sort of deep thing to grab or grasp around, but there is a need for educating. So I call it think quantum, but it's like it can be explained in a way that is understandable for people as well, and those will have a more positive impact on the society overall. Because if we don't do it, then it stays in the mystic realm, and then it starts becoming more of a fear factor than a friend as such. So I think those would be important.
Yeah, I love that Arthur C. Clarke quote. I actually have I have a separate video cast that I do, which I took his quote from the title. It's called "Indistinguishable from Magic," and often when I'm trying to explain emerging technologies to some of my colleagues, that is what I kind of have to fall back on is just consider it magic. We try to explain it anyways. So wrapping things up, I understand that you're going to be attending the IQT Vancouver Pacific Rim conference coming up June 4th through 6th. I don't know if you're both going to be there or just one of you, but
most likely myself. We have a lot on plate for all of us, so I'm sparing the travels for Janne in many cases as much as I can.
So Himadri, what are you most looking forward to about the conference?
I personally, I am really excited about the Canadian and North American ecosystems. So I'm very keen to get involved. Like I said in the beginning, we are very open to collaboration. We want to collaborate. We already have a collaboration with a company called CMC Microsystems in Canada regarding our processors and our devices. I would like to expand it more. I want research community to know about us, to learn what we are able to provide them, to see the benefit of it and work with us. So that's one aspect. And the other aspect for that specific conference, being a Pacific Rim, I think it's also important to understand that semiconductor and quantum are not necessarily two different streams. They are pretty much close to each other, and we should leverage one for the other. And this is the kind of message I'm going to try to send across, that let's combine the expertise on the other side of the Pacific Rim on semiconductors with the quantum expertise on this side of the rim and build it together as a collaboration.
So one final question for both of you. What do you most want the average person who's not a scientist, not a technologist, just someone who is working in the field and often works with computers, what do you want that average person to understand about the quantum computing field?
Yeah, well, the message would be more that quantum computers are coming and they will bring disruptions to the world as we know it. They are not better classical computers, but they can solve problems that are now unsolvable and make the things that we are doing now much more efficient, making everybody's life better and easier. So this can affect the world to make it better in many respects.
And what I would add on that is the story that I love telling to people is look at the classical computing industry and how it was born. It was 70 or 80 years ago when we had a room filled of ENIAC machines, right? So that's where we were 70, 80 years ago. And then with the birth of with the birth of integrated circuits, we came to the phase of personal computers, and that was in the 80s. And we started working with our Commodores and stuff like that. And then now we are with our mobile phones, which are more powerful computers than they were 30 years ago. And the quantum computing path will go that way. We are still in the ENIAC stage of quantum computing. So we hope that SemiQon would be the one which builds the quantum integrated circuits and brings the change in the field. And then what happens after that, we don't know. I totally agree with Janne. The potential is enormous, but we will see how it goes.
Well, Himadri and Jan, this has been great. Thank you for joining us, and thank you for taking your time out to come talk with us. This has been a DeadCatLiveCat videocast. Thank you for watching, and we look forward to seeing you, Himadri and Jan, at IQT. Well, Himadri at IQT, and we look forward to seeing all our viewers again on our next interview.